Today we will show how to use response spectrum analysis to find the seismic design forces for multi-story buildings. In order to explain this topic, first we will need to explain the free vibration of a multi-story building. Then we will show how a multi-story building responds to a dynamic loading such as an earthquake. Finally, we will show how we can use the response spectrum curves to find the design seismic forces for a multi-story building. A multi-story building is a multi-degrees of freedom system, which means that it can have more than one independent degree of freedom. For the shown 3 stories building, for example, there are 3 degrees of freedom in the x direction, because each story can move in the horizontal direction independent of the other stories. In other words, there is no constant relation between the horizontal displacements of the 3 stories. Now let us examine the free vibration of this 3 stories building. If we apply a force to the building, it will be displaced, and after removing the force, the building will start to move in a free vibration motion. In order to study this free vibration, we need to know the natural time period, which is the time needed to complete one cycle of vibration, and we need to know the shape of the vibration. By exploring the free vibration of the multi-degree of freedom building, we will find that the vibrational motion is a complex motion that is actually a combination of several basic shapes called the mode shapes. The shown 3 stories building, for example, has 3 degrees of freedom in the x direction, 1 at each story, and therefore its free vibration will be a combination of 3 basic mode shapes, and each mode shape will have its own natural time period. In each mode shape, there is a definite relation between the displacements at the different stories, U1, U2, and U3. In other words, the 3 displacements are not independent of one another. If one displacement is known, the other 2 displacements will be automatically evaluated. So when the structure is vibrating in a certain mode shape, in effect, it is acting as a single degree of freedom system. By decomposing the complex motion of the multi-degree of freedom structure into a combination of basic mode shapes, we are in effect changing the multi-degree of freedom system to a number of single degree of freedom systems. The number of single degree of freedom systems is equal to the number of mode shapes. For the 3 stories building, the free vibration motion in the x direction can be represented as a combination of 3 single degree of freedom systems. Each of these systems vibrate in a definite shape called a mode shape, and each system has its own natural time period. Now let us study the response of a multi-degrees of freedom building to a dynamic loading such as an earthquake. If the shown 3 stories building is subjected to an earthquake force at the base, it will respond in a complex motion as shown. Similar to the free vibration, this complex motion is a combination of motions that has definite shapes called the mode shapes. In fact, these are exactly the mode shapes found in the free vibration. For the 3 stories building, the response in the x direction will be a combination of 3 basic mode shapes. Each mode shape will have a certain share in the final response. This share is called the mode participation and can be measured by a factor called the mode participation factor. In summary, in order to obtain the response of the 3 stories building, which has 3 degrees of freedom, to an earthquake, we can convert the building to 3 single degree of freedom systems, each system vibrating in one of the basic mode shapes. By combining the response of the 3 single degree of freedom systems, we can obtain the final response of the building. This process of decomposing a response into the basic mode shapes is called modal analysis. Modal analysis needs a separate lecture to explain it in details, but for the purpose of this lecture, we will just summarize it in the following steps. The first step in the modal analysis is to analyze the multi-degrees of freedom building to obtain its basic mode shapes and natural time period for each shape. Typically, we can obtain a mode shape for every degree of freedom. The next step is to analyze the effect of the earthquake loading on the building several times, each time assuming that the building is following one of the mode shapes. When the building is following a definite mode shape, then it will act as a single degree of freedom building. Therefore, in this step, in effect, we are converting the multi-degrees of freedom building to a number of single degree of freedom systems. The number of single degree of freedom systems is equal to the number of mode shapes. For each mode shape, we calculate the modal participation factor tau. The response of the building for each mode is obtained by multiplying the result of the single degree of freedom analysis of that mode by the participation factor of that mode, tau, multiplied by the mode shape phi. The final response of the building is obtained by adding the responses of all the mode shapes. So, what are the benefits of modal analysis, and why do we want to use it in the first place? Because the modal analysis is changing the multi-degrees of freedom into several single degree of freedom systems, then we can benefit from all the advantages of the single degree of freedom analysis. The analysis becomes simpler and faster. More importantly, we can apply the methods of the analysis developed for the single degree of freedom structures to multi-degree of freedom buildings. Therefore, we can apply the response spectrum analysis to multi-degree of freedom buildings using modal analysis. One major problem of the modal analysis, however, is that it is based on superposition and therefore it is not suitable for nonlinear analysis. Now, let us explore how to use response spectrum curve with modal analysis. Suppose that the 3 stories building was subjected to an earthquake and that we analyzed the first 3 modes of vibration, mode 1, mode 2, and mode 3, and obtained the full response of each mode to the earthquake motion, acceleration versus time, as follows. We can easily obtain the final response by combining the 3 modal responses. Now, suppose that we don't have these complete responses available, but we only have the response spectrum curve for this earthquake. How can we find the final response? As explained in detail in a previous lecture, the response spectrum curve gives you the maximum expected response of the building to a certain earthquake based on the natural time period of the building. This maximum response is called the spectral acceleration. However, because the building is multi-degrees of freedom, it has more than one natural period. It has a natural period associated with each mode shape. Therefore, the response spectrum curve will give us a maximum response for each mode of vibration. However, the response spectrum curve will not tell us when does this response happen and whether it is directed to the left or the right. If we locate the maximum response on the complete response that we obtained earlier, we will find that these maximum responses don't occur at the same time, and they are not all in the same direction. Remember that to obtain the complete response, you need to do a complete modal analysis. The response spectrum curve will not give you this information. So how can we combine these maximum responses to obtain the maximum response of the multi-story building? We cannot just add these values because they may occur at different times and may have different signs. There are several methods proposed in the literature. The first method is to add the absolute values of these modal responses. Using this method, you are sure that the obtained value is higher than the real maximum, but this method is very conservative and will lead to a waste in design. Another popular method is the SRSS method. In this method, we calculate the summation of the square of each model response, and then we calculate the final response as the square root of the obtained sum. In some cases, the obtained value using this method might be lower than the real maximum, but this is considered an acceptable approximation, and there are some rules in the code that try to limit the effect of this shortcoming, as will be shown later in the lecture. Other approximate methods of combining the maximum model responses are found in the literature and can be used. In the rest of this lecture, we will use the SRSS method. The steps required to analyze a multi-story building using response spectrum can be summarized as follows. First, we obtain the mode shapes for the building and the natural time period corresponding to each mode shape. Next, using this information, we can calculate the participation factor tau I for each mode. At the same time, since we know the natural time period for each mode, we can obtain the maximum acceleration occurring for each mode due to earthquake. This is called the spectral acceleration for the mode SAI, where the subscript I indicates the mode number. To obtain the response of each mode to earthquake, we multiply the spectral acceleration for that mode SAI by the participation factor tau I and the mode shape phi I. To obtain the final response of the building, we combine the response of the different mode shapes using SRSS method or any other acceptable method from the literature. Now let us look at an example. We have a 3-story building which is formed of ordinary concrete frames, so the response factor R is equal to 3 according to ASCE7-10 Code. The response factor R is a factor used to change the results obtained using a linear elastic analysis to its equivalent non-elastic response. The building is residential, so the important factor I is equal to 1. Although ASCE7-10 Code is used here to obtain the seismic factors as well as the response spectrum curve, most of the procedure explained in this example is valid for all other design codes. For this example, we will only consider the motion in the y direction. The motion in the x direction will follow the same procedure. The weight of the different stories is as shown. To obtain the masses, the weight is divided by the acceleration of gravity g. The first step in our analysis is to obtain the mode shapes of the free vibration and the corresponding natural time period for each mode shape. We can obtain the mode shapes manually using the eigenvalue or the Ritz method, or by using a structural analysis software. We need a separate lecture to explain these methods, so we will go ahead and directly present the obtained mode shapes. In the y direction, we have 3 mode shapes of free vibrations. Mode 1, vibrating with a natural time period T1. Mode 2, with a natural time period T2. And mode 3, with natural time period T3. As a start, let us focus on mode 1. The ordinates of the mode shape is as follows. 1 at the first story, 6.83 at the second story, and 7.55 at the third story. Note that these ordinates represent a shape which is a constant ratio between the displacements of different stories. Another valid solution for the mode shape would be 10 to 68.3 to 75.5 or 100 to 683 to 755. Any of these solutions are valid and will eventually lead to the same final response. For this mode shape, the natural time period T1 is equal to 0.282 seconds. Using the mode shape ordinates and the story masses, we can calculate the participation factor of this mode, tau1, by dividing the sum of the product, mj, times phi j1 by the sum of the product mj times phi j1 squared, where mj is the mass of the story j and phi j1 is the ordinate of mode shape 1 at the story j. For each story, we multiply the mass of the story times the ordinate of the mode shape at the story as shown. Next, we multiply the mass of each story with the square of the mode shape ordinate at that story. We find the summation of both products, and then we calculate the participation factor tau1 by dividing the first summation by the second summation. The next step is to obtain the spectral acceleration for mode 1. However, in order to complete this step, we need to construct the response spectrum curve. Assuming that this building is located in New York City and that it is founded on very dense sand, we can obtain the seismic factors and draw the response spectrum curve using the tables and equations from ASCE7-10 Code. This process is explained in detail in a previous lecture on response spectrum analysis. Now that we have obtained the response spectrum curve, we can use it to find the spectral acceleration of mode 1. Recall that the spectral acceleration of mode 1 is the maximum expected acceleration that would occur due to the earthquake if the building is restricted to only vibrate in the shape of mode 1. By locating the time period t1 of 0.282 seconds on the curve, we can obtain the corresponding spectral acceleration for mode 1, SA1, which is found to be 0.222 g, where g is the acceleration of gravity. In the next step, we need to obtain the seismic forces at different stories for mode 1. To do that, we need first to obtain the maximum expected acceleration at each story for that mode. The maximum acceleration at any story, J, is equal to the product of the mode participation factor, tau1, times the spectral acceleration for the mode, SA1, times the ordinate of the mode shape at that story, phi J1. The seismic forces at any story is equal to the acceleration at that story multiplied by the mass of the story. We then repeat the same procedure for modes 2 and 3 to obtain the seismic forces for these modes. For each mode I, we obtain the participation factor tau I and the spectral acceleration SAI. We use these values to obtain the story accelerations and the seismic forces for each mode as shown. Now that we have obtained the spectral seismic forces for each mode, we need to combine these modal forces using an acceptable method, such as the SRSS method. However, we need to point out some important issues regarding this process. For each mode, we can apply the principle of statics and the equilibrium equations on the modal forces to obtain any straining action or displacement in the building. For example, for any mode, we can sum the modal forces to obtain the base shear for that mode, or we can take the moment of the forces about the base to obtain the modal base moment. We can obtain the final values of the base shear or the base moment by combining the modal values using SRSS. Take care, however, that we are not allowed to use the equilibrium equations on the combined values of the forces or straining actions. We cannot, for example, combine the model forces at each story and then find the base shear on the combined model by taking equilibrium using these combined values. Another important point to consider is that the combined values of the straining actions are absolute values and have no sign. Therefore, the designer should assume that the combined straining actions might act in the positive or the negative directions. Now, let us practice and do some combinations. First, let us calculate the shear in the third story, V3. To do that, we need to calculate the third story shear for the first three modes, V31, V32, and V33. Then we use SRSS method to combine these three values as shown to obtain the value of V3. Next, we will evaluate the shear in the second story V2. To do that, we need to calculate the second story shear for the first three modes, V21, V22, and V23. For any mode, the shear in the second story for that mode can be obtained by applying the equilibrium equations for that mode as shown. The final value of V2 is obtained by combining the model values using SRSS. Finally, we will evaluate the base shear for the building, VB. Again, the same procedure is used. The base shear for each mode is evaluated using the equilibrium equations. Then, the model values are combined using SRSS. Notice that the obtained combined values are absolute values and can act in either the positive or the negative direction. Therefore, both directions should be considered in the design. If we divide the base shear for any mode, I, VBI, by the spectral acceleration for that mode, SAI, we obtain a value called the modal mass, and we will give it the symbol MMI, where the subscript I indicates the mode number. One very interesting property of the modal mass is that if we sum the modal masses of all the modes, we will find that the result is equal to the total mass of the building. If we divide the modal mass of any mode by the total mass of the building, we obtain a property called the modal mass ratio. The modal mass ratio of any mode is a measure of the importance of that mode in the final response of the building. If the modal mass ratio of a certain mode is very small, this means that this mode is not significant and can be ignored. The modal masses of modes 1, 2, and 3 are calculated as shown. It can be seen that the sum of modal masses for the three modes is nearly equal to the total mass of the building. The modal mass ratios are also calculated. The modal mass ratios for modes 1, 2, and 3 were found to be 78.4%, 8.8%, and 12.4%. This indicates that mode 1 is the most significant mode in the final response of the building. Finally, we want to explore several rules stipulated by the ASCE7-10 Code to regulate the response spectrum analysis of multi-story buildings. The code requires the spectral straining actions to be multiplied by the importance factor I to consider the importance of the building during the design. The straining actions obtained earlier using the response spectrum analysis are elastic values that are typically obtained from a linear elastic analysis. Therefore, the code also stipulates that the obtained straining action values be divided by the response factor R to convert these actions to their equivalent in elastic design values. The code also includes a rule which governs the number of modes that should be included in the response spectrum analysis. According to the code, the sum of modal mass ratios of the modes included in the analysis should be at least 90%. In our example, the modal mass ratio for mode 1 is 78.4%, which is less than 90%. So mode 1 alone is not enough. Other modes should be included in the analysis. The sum of modal mass ratios for modes 1 and 2 is 87.2%, which is still less than 90%. Therefore, according to the code, more modes should be considered. The sum of modal mass ratios for modes 1, 2, and 3 is 99.6%, which is higher than 90% and fulfills the requirement of the code. Therefore, according to the code, modes 1, 2, and 3 should be included in the analysis. Because the response spectrum analysis involves approximation, the code requires that the base shear obtained from the spectral analysis be calibrated against the base shear obtained from the equivalent method of the code. The spectral base shear should be at least 85% of the equivalent base shear. If the spectral base shear is less than this limit, it should be multiplied by a scaling factor to increase it so that it fulfills that limit. All the design values obtained from the spectral analysis should be scaled up using this scaling factor. If we apply this calibration to our example, we will find that the spectral base shear is less than 85% of the equivalent base shear. A scaling factor of 1.07 should be used to increase the spectral base shear so it fulfills this limit. All spectral design values should be scaled up using this scaling value of 1.07 to obtain the final design seismic values.